Hello and welcome. Bonjour et bienvenue. Today's tutorial is intended for my science colleagues, going a little deeper into how we can use the solver add-in in Excel to do some interesting fitting exercises. More specifically, I'd like to illustrate how solver can be used for fitting, even for a system where we do not have an explicit equation. So an excellent example of such a system is the product formation kinetics for an enzymatic reaction that goes to completion. Now, the Michaelis-Menten equation works well for describing reaction rate at a given concentration of substrate if we know the parameters Vmax and Km. However, we do not have an integrated form of the Michaelis-Menten equation that tells us the concentration of product that we would observe at any time point over the course of the reaction. But even in the absence of this explicit equation, we can do some empirical numerical modeling to predict the concentration of product that would be observed. And we can use these values to fit for Vmax and Km. So let me show you what I mean. This spreadsheet resembles the one I showed in a previous video, Intro to Fitting, where I have written the model at the top strictly for annotation purposes, and I've set up the cells that contain the parameters for the equation, two of which will be fitted, Vmax and Km, and I've prepared columns for the measured kinetic data, time and product concentration. The big difference with this spreadsheet compared to the last one is in the formula for the predicted value. So without an explicit equation, we cannot directly calculate product concentration at any time t. However, we can calculate the instantaneous rate that would be observed at each time point, and we can multiply that rate by the duration of the last time interval to give the concentration of product that would be formed over that interval, and we can add that concentration to the concentration of the product formed at the end of the preceding interval, and so we can continue to add an incremental concentration of products right to the end of the data set, right to the end of the reaction. So the formula at the heart of this modeling would start with the concentration at the last time interval, so C13, plus the time interval times the spontaneous rate. So the time interval is A14 minus A13, and the instantaneous rate is given by the Michaelis-Menten equation, Vmax, so that's D4, let's make that absolute, times the substrate concentration. Our substrate concentration is going to be given by the initial substrate concentration, D6, absolute, minus however much substrate has already been consumed. And that would be given by the amount of product formed over the last, up to the last time period. So minus C13. Divided by Km plus concentration of substrate. So Km is given by D5 absolute plus concentration of substrate remaining, so the initial concentration absolute minus the amount of product formed up to the last time point. Now when I double click the lower right hand corner, it fills in all of the cells, and you can see that I already set up this graph to show the predicted values. And you can also see that the predicted values are not very close to the observed values, but solver will fix that for us. So now we have to calculate the residual, which is simply predicted minus observed. And we can copy that down. And now let's add a statistical calculation. So the deviation of a data point is defined as its distance from the average value for the data set. So this would be B13 minus the average of B13 down to B113. And let's make that an absolute array. And now copy down. Now the sum of squares of the residual is given by sum SQ of the residual array, Control Shift down arrow, close bracket, return. And the sum of squares of the deviations, or called the total sum of squares, is equal to sum SQ of this array, E13 down to E113, close bracket, return. And this allows us to calculate the correlation of the fitting, R squared, as 1 minus the ratio of the residual sum of squares over the total sum of squares. So now let's fit using solver. So we go to data, solver. So the objective cell is the residual sum of squares, D10. And I want to minimize its value by changing the value in cells D4 and D5, namely Vmax and Km. Now Km is never negative, and neither is the rate of product formation, so I will set these otherwise unconstrained parameters to be non-negative. When I click solve, solver has found a solution. It is converged, so I click OK, and solver has now replaced the values of my initial guesses for Vmax and Km with the final values that minimize the residual sum of squares. We can see that the residual for each data point on this residual plot is scattered randomly around 0, and that the best fit line passes nicely through the data points. Finally, the R squared correlation for this fitting is 0.996, which is pretty good considering the noise in the data. So to summarize, we learned that we don't need an explicit equation for fitting. We just need a way to generate predicted values based on variable parameters. So in this case, we calculated incremental changes in product concentration over each time interval based on instantaneous rates that we calculated with the Michaelis-Menten equation. And that's the equation that used these parameters. We also saw how to calculate the R squared correlation as a measure of the goodness of fit. And it may be of specific interest to some viewers to note that for a single enzymatic reaction, starting with a high concentration of substrate that goes all the way to completion, we can use the kinetic data of the product formation over time to fit for Vmax and Km from one kinetic run. Now, this can be a really valuable approach if the substrate or enzyme you're studying is so precious or expensive that it is impractical to measure multiple initial rates and define a Michaelis-Menten curve in the traditional fashion.